So hey everyone, I think we can start now. Am I audible?
Yeah,
Guys,
you're audible.
Yeah, fine, thank you. So audience, be responsive and be active. If you have doubts throughout the session, uh, just put it in the chat or you can unmute yourself and you can ask us. We are ready to solve. So let us start the session now. I am Karthik Sainath Reddy from third year CSE Cybersecurity Department and I am core team member of Robotics Club Sastra. So today's session, we will be discussing about so anyone say the topic name first? Someone like even in the chat.
Designing of a robotic system.
Yeah, design of a robotic system. So this is day 9 of our summer school and today's topic is designing of a robotic system. And here is the next slide. So what exactly designing a robotic system mean? So this is a question for you. Think like see this question clearly and try to answer like what you are expecting today. Like what you are thinking about designing a robotic system exactly mean? Like
Forming the skeleton of a robot.
okay. So any more answers? Like put it in the chat box. There is actually no exact answer, but you can put your thoughts in the chat box. I will say whether which is similar or familiar to the answer or not. Planning. So Akash Yadav, planning what? Karanya Krishna saying basic structures. Okay. Yeah, you're going good. Yeah, try. Keep trying. Like you will get some answer actually if you analyze the name perfectly. I mean, if you study the name correctly, each word you will understand what we are trying to say. Planning of robotic components to be used. Yeah, that is one of the near closest answers. As I told, there is no exact answer like how to design every robot in a single statement, but we have a specific procedure actually. Okay, so let us move to the next slide. So it is going to be a six steps process actually. Think of A to Z robot. Okay, fine. So this is going to be a 6-step process. I'll explain what I mean designing a robotic system means. Imagine I'll give you a problem statement like you have to do a specific work. For that, I want you to design a robot actually. Suppose you are writing an exam, like suppose you are writing any assignment or you are writing on some book. If I ask you to create a robot for that, you can directly create a robot from scratch actually. You need to do some analysis to do some work. You have to follow some procedures, check for the feasibility of the robot. You have to get components and a lot of things are there. So to create any robot you want, you need a specific procedure which has to be followed. So the procedure we are going to follow is a 6-step process, and this is what exactly designing a robotic system mean. So if you want to build a robot, you need hardware, you need people to code, you need to connect, you need actuators and motors to turn the joints and all, depending on the specification or the need you want. So suppose we will consider one thing. Yeah, let us take a table fan. I hope everyone know table fan, right? Everyone knows table fan, or should I explain what exactly a table fan is? Guys, respond. I'm just asking for fun to confirm whether everyone are not sleeping and still listening to the content what I'm speaking. Yeah.
Guys, adding to Karthik, please unmute yourself and try to speak. So we'll have a more interactive session.
So, okay. We'll change the question then. If there are no answers, I will change the question. Do you think table fan is a machine or robot? Guys, anyone answer? Is table fan a machine or robot? Okay, machine. If I say it is a robot, then people will definitely beat me. I am sure of that. Yeah, machine. Okay, fine. This is a machine. And suppose I want you to turn the table fan as a robot. Like we want to make this table fan completely as a robot. It has to follow a person. Suppose there is a table fan in one corner of the room and a person is roaming in the room. So the main objective is the table fan's orientation has to follow the person moving in the room, like a sunflower following the sun. So, okay, so now I gave you a task actually. The task is you have to convert a table fan into a robot. What are the things you will do? Like how you will convert a table fan into robot? I'm not asking about exact answer. What I am asking is what is your perspective when I say make it as a robot, like make a machine as a robot? What is your perspective? Like what are the things you will be using or anything? Like what is your view? Yeah, we can connect a microcontroller and voice controller to access it. Okay. Sensors. Nice. Yeah, like analyze more. You are getting into the field, analyze, try to analyze more. Even remaining people also try to tell the answers you are feeling. Like which maybe that may be the best solution. We can't expect that. So everyone try giving some answer. Exactly. Voice controller, even yesterday while we are discussing, I didn't thought of voice controller and all, but that's actually a nice idea and like appreciable analysis of the statement. It is similar to a manipulator. Piezoelectric sensors and all around the floor. Awesome. Yeah, move on, move on. Like you are getting better ideas than us. I am pretty much sure of that, and still think some more near. Yeah, you are moving correctly. Fine. Okay, any more answers? I'm waiting for answers, like some more answers. Even if anyone wants to speak, you can unmute yourself and speak. There is no objection in that. PIR sensor to detect motion. Okay, you listened you observed the problem statement exactly. Okay, got it. Fine. Let us move to the content then. So first thing when I say we want to convert any machine to a robot, first we have to analyze what is the situation where I want to turn that table fan as a robot. Depending on the situation, we have to use. Now we have a lot of sensor suggestions actually here. IR sensor, PIR, piezoelectric sensors, and microcontrollers. A lot of things are here. See, now let us analyze the situation first. So let us go for the first one. The first one is defining the problem, which is like analyzing the objective correctly. So currently our objective, it is like the table fan has to follow the person who is moving in the room. So actually we know our table fans can rotate, but not greater than 180 or 170 degrees, right? So the table fan's head has to follow a person. And now we have analyzed the problem statement, but see, inside a room, if you are using any temperature sensors, like if the sensor can detect the objects based on the temperature radiation they are releasing, there may be hotter objects better than humans in the room and it may detect it as an object. So in this analysis, what we can say is we can't use temperature sensors all over the room to detect a person. Even maybe if it is on summer, some metal objects will have more temperature than human body. So they will produce more heat. This temperature sensor will think like that is an object, and imagine if there is a chair which is giving more heat, then the fan will continuously point to that chair instead of moving person. So this is like this statement will say like the temperature sensor can be used in this situation. So this is one type of analysis, like analyzing what types of sensors we will be using. And there are a lot of another sensors are also there. Yeah, we got a lot of suggestions in chat box and I'm very happy for that. So one more suggestion is we can connect a microcontroller and voice controller to access it. So if you connect a microcontroller and voice control to access it, see if the person is moving very fast or very random, you can't give voice control each time. Like I am on right side, I'm on left side. You can't give voice control every second. So that idea is also okay, but not efficient. We have few more efficient ideas there. Does anyone have any more ideas? But I got a lot of unexpected answers from the chat box. which are seriously and highly appreciable. So anyone thinking of any more ideas? It's okay. So am I going too fast? Like my English is too fast or is it normal? Can anyone respond for that?
Normal है.
What, bro? No, sorry, I didn't get that. Normal, okay, okay, fine. Got it. And yeah, let us move to the second step. So as soon as I told you to turn the table fan into a robot, so the first step is we have analyzed like what sensors we have to use. Now the second thing is research and designing. In this research and designing, we have few subtopics like some steps to be followed in the second step. And this is gathering information. And second one, identifying the design required. Third one is identifying possible and alternative designs. And fourth one is planning and design. Yeah, let us analyze each of these points actually. So when you select a sensor first, uh, go to Google and search for the sensor, see what it can do, at what situations it will fail, and if that situation is exactly in that room, like in the environment you are making the robot, then you can't use the sensor. See, let us consider the example of these temperature sensors. So first, as soon as if you get a thought of using a temperature sensor when converting this table fan into a robot, go to Google and search for temperature sensor where we can use it and where it fails. Obviously, you can see some statements stating it will detect all the objects with high temperatures, like depending on temperature, it will detect the object, right? So in that situation, you have to think of another sensor. So same like depending on the situation, depending on the sensors which are running in your mind, search for all the sensors. First, think of using that sensor. Check for what are the drawbacks if you are using that sensor, and then go for another one. And here, that is the same we are stating in these 4 steps. When you see the third step, you can see optimization check actually here. Optimization check means, yeah, you can build it even using IR sensors actually. See, my analysis when I listened to this question for the first time is, we will put 3 sensors in the room, like one in one corner, second one in another corner, and third one in the middle of those 2 on the wall. So if the person is detected in first sensor's range, the fan will turn in that direction. If the person is detected in third sensor's range, the fan will turn into that direction. Like that we can use, but still there is a bug here in this solution actually. What if there is a hot object in between that area? So like that we have to optimize the solutions. First start thinking of a solution, then continue optimizing it. Yeah, so that is the second step. And third step is creating a prototype. So can anyone know what can anyone give it a try? For the question, what is the difference between prototype and a model? Like a project, a complete robot and prototype. What is the difference? What do you think? Like I don't say you all have the answer for this question, but what do you think about this difference, prototype and a machine, like the robot? Yeah, I'm waiting for the answers, and if anyone want to speak the answer like lazy to type, you can speak directly. Honestly speaking, I am also lazy to type. That's why I continuously speak. So you can unmute yourself and you can speak. What is the difference between prototype and a direct project? Creating first design. Okay. Like what do you mean by first design exactly? Prototype is like a blueprint. Yeah. First version. Exactly. Okay. Prototype just a functional part which is not fully designed. Yeah. Correct answer. So anyone want to give any another definitions for prototype? It's okay. So yeah, that is exactly what the prototype mean. Getting close, awesome. Yeah, exactly. We are getting better responses than I expected in the chat box actually. Yeah, so let's go to the prototype thing. Prototype is like we'll be creating a blueprint actually. No, the prototype is not exactly the original model. Okay. Let us dive into the topic. So yeah, let us go with an example actually. Imagine you have to create a robot. You have to create a robot. Now the table fan itself. Instead of directly playing with a table fan, what you can do is you can take some servo motors, some components, some Arduino boards, build it in small size, like you will be scaling it down to 0.1x or something, so that you can test it better. You can test all the features you want, and then you can implement it for the original model. So this is like a sample model. Yeah, exactly. To simply say, it's a sample model. So we will be scaling down, or we will be making the blueprint, or you can say it is like a simple model, not the exact original product we want to deliver. So that is the prototype. So if you want to create a table fan, turn a table fan as a robot, what you have to do is you have to create a prototype first. Don't create a prototype which is of same size of a table fan. What we will do is we will create this prototype in like a size of our arm or some hand or something, a small size with some servo motors, some Arduino boards and all, whatever you want. Like this depends on solution you are thinking, even the sensors also. So that is the third step, creating a prototype. Yeah, so let us go for the fourth step. The fourth step is programming and testing. So in this programming and testing, what we will do is we will connect all the sensors. We will connect all the components like motors, these H bridges, some drivers and all to the boards. We will build a prototype. Now we have to write code for that prototype. So if you are, it depends on the board you are using. Specifically, if you are using this Arduino boards and all, you will be moving with C language, that Arduino programming and all, and it depends on the board. So if you are using any cameras and all, you can write code for that. Some boards will accept Python to run on them, and in that case, you can use Python. It depends on the board you are using for that prototype. And one more thing I forgot to mention. This step, creating a prototype, is there, right? So in this session now today, we will be showing you some prototype, but in simulation. Simulation is like if you want to build a robot, instead of spending thousands on robot, first we will do it on a simulation. Simulation means you will have freedom to do whatever you want in that specific temporary world in your laptop or system. So we will be doing simulation, and then if that simulation is successful, then we will go for hardware prototype, and then we will go for original model. So the fourth step, we have finished programming and testing. Like you will upload a program. If the program don't have any errors, it will run. The prototype will work fine, and you can upgrade. Like if you want to add more features, if you want to update the values and all, it depends on the situation. You can update, and this programming will work. Like you will change the programs and upload to prototype. So the next step will be building your robot. Like you can begin that construction works now. That means if your prototype is successful, like you have made a robotic table fan which will turn around for the person, which is of your hand size, like a small size. If it is successful, then you can get the main big components, and you can explain, like you can create the main model now. And the sixth one is evaluating your robot. So as soon as you finish building your robot, you can directly test it. You can see its performance, its power consumption, all the factors you want. Like if you put the table fan, imagine like now the current table fans we have, those table fans can't turn more than 180 degrees. But this time, now we can, if you attach some motors or some revolute joints like that, you can make the table fan turn 360 degrees. It is also possible if you can create such design. So that is like evaluating your robot. So we can, so now what we have discussed is we tried to turn a table fan into a robotic table fan, which can follow a human. You can use the sensors to detect a person moving in the room, and you can use your voice controls as given in the chat by someone. And okay, so using that voice controller, they can say, they can stop the fan, they can start the fan, they can increase the speed, or whatever the features they can implement. And the next step, okay, so let us quick revise this thing. So we defined the problem, the table fan, turning table fan as a robot. The second one is research and design. We have searched for sensors. We have analyzed a lot of sensors, and we have observed like which sensor can be used in which situation. It depends on the environment where we are building the robot. And the next step is creating a prototype, which is like a sample machine you are trying to do. The fourth one is programming and testing, which is like coding and implementing. If there is any error, code again. If there is any error, code again until you get the perfect working. So the next one is building your own robot. Like you can build it with main components and all the real world things you want. And evaluating your robot. Like if you want to improve performance, you can come back to step 3 and then you can do again. Like suppose you have used a motor with power 10 units exactly. If you are not, and you are at step 6 now. But if you are not satisfied with that motor with power 10, you can replace the motor and you can check everything from step 3. So that if you can have any optimizations, you can optimize. Yeah, so that's all from my side. Now Banu Chandana will show you the simulation actually. If how many of you know about simulations? Like what exactly a simulation will be? Anyone have any idea?
To perform a code in a software.
Yeah, performing a code in a software. Okay. Any more answers? Chat or direct mic option, anything is fine. Audience call. So try for any answer for 1 minute. Like I'll wait for 1 minute and then I will explain you what a simulation is and then you will see the simulations. Okay, I think there are no answers for this. Okay, 3D models. Fine. Okay, fine. I will break the silence then. See, simulation is it is like testing your idea in a virtual world exactly. Yeah, we will have a virtual world where you have freedom to do whatever you want. Imagine like you want to build a robot actually. You want to build a robotic arm or you want to build some model, some construction, any design. What you will do is you will construct it in 3D or 2D depending on the specification and you will execute that model in a simulation world. Now this table fan idea also what we can do is we can create a table fan 3D model. We can attach those revolute joints and all to turn the table fan. We can we can test we can attach the sensors to the fan or in the simulation world and we can write code for that. And all these things we can wrap it up and then we can run it in a virtual world. That is exactly what simulation is. And for robotic simulation, we mostly use this software named Coplea Sim. I will put that software name also in the chart. That is Coplea Sim. So now we will see the demonstration of how this Coplea Sim works. Bhanuchandana, you can share the screen.
Yeah.
Guys, and one more thing, do we have any doubts or re-explanations up to this part? Anyone, like even in a silly doubt, whether like you can use that sensor or not, any silly doubt. If you have any doubt, put it in the chat or ask. We will solve. Okay, if you have no doubts, put no in chat box and Banu will start. Okay, Banu, start.
Yeah, guys, can you see my screen? Hello?
Yes, I will be able to.
Yeah. So can you see the screen, right? Like, okay. Visible. Okay. So yeah, as Karthik said, the simulation means we'll be having some robots which are developed inside, virtual environment. We'll be having the dynamic interactions between the robot. See, in real world, we can't always start by building a big robot and do the interactions with the environment around it, and we can't redo it again. For example, let us take a robotic arm, something like this. Yeah, we can't build this robotic arm directly, and we can't always, do experiments with it freely because it takes a lot of money, time, and effort to build it. And also, we can't, have the freedom to move it as we wish. Like we need to spend a lot of effort. But in simulation world, we need not to do all that stuff. Like everything is done in virtual environment, and by this we can also calculate how. By this we can get an idea like how it will interact in real world also. That's the main idea of simulation. So this is a Coplea Sim. So this is like a Coplea Sim software we are using. This is used for robotic simulation for both research, industrial, and study education purposes. So here these are like the robots which are pre-built, and this is like UI, how it looks and everything. So this is like simulation. So we'll be starting the simulation and all. So guys, do you know what's the difference between a revolute joint and a prismatic joint? Any answers? Like you can keep in chat box, or you can speak.
Guys, in previous classes, we have explained like what a revolute joint and prismatic joint means. Like you can give it a try, like you can try to recollect and answer for this question.
Yeah, we have many different types of joints, right? Prismatic joint, revolute joint, spherical joints. So do you have any idea what's the difference between these joints?
If the answer is lengthy to speak, unmute and speak. No problem.
Okay, then let's move into it. Okay, so prismatic joint. Prismatic joint is a joint where you will be having a to and fro motion, and a revolute joint is where you will be having the rotating motion, like you have like a 360-degree of rotation in it. So in this, we have built a simple. We have built a simple structure which is made up of like two blocks, and we have kept here a prismatic joint, and we kept here a revolute joint. So let's try simulating it. See, as you can see here, in a prismatic joint, it's going like a to and fro motion. But in a revolute joint, it's like a revolving. You got the difference, right? So this is what a prismatic and revolute joint is. So these are the basics of, before you are doing a simulation, you need to know like what are the joints, and what are the sensors we'll be using and all that stuff to get an, you can build your own model by all this. So next one is like vision sensor. Let me show you. So guys, can you see this?
Banu, one stop the simulation and try. No. It is working fine. Stop the simulation once.
So now we'll be talking about sensors. So do you know what's the difference between vision sensor and camera? Any idea like what's the difference between vision sensor and normal camera we use? No. Okay. Can you try by the name? Like, what do you feel it will be like? Why do we need to use the vision sensor when we have cameras? Specific resolution, correct? Yeah, you're moving to a very close answer. So yeah, as Avantika said, vision sensor is used for fixed resolution, but for camera, the resolution is adjusted automatically. So that's the main difference between vision sensor and camera. So we need not to use camera every time. We can use vision sensors also for building our boards. So here I'll show you how to add a vision sensor. So here you will be going and adding a vision sensor. In vision sensor, there were two types. One is orthographic and perspective. So I'll be showing you which is what. So this is a perspective vision sensor. So look at these lines, right? Perspective means it's having a wide range of angle. Starting from 0, it's having an angle. Okay, this is like perspective vision sensor. And here I will be adding a floating view.
Banu, select the vision sensor. Okay. Wait.
1 second.
Okay, now click right click.
Yeah, so see this. when we simulate this, the vision sensor, it's showing like, top view, whatever. Can you see this image, right? So this is the image we'll be getting at this vision sensor. So this is like a pixelated image. It means that this vision sensor has the resolution of 32 by 32. So when we increase the resolution, that is from 512 to 512, and when we redo the simulation, we can get the clear image. So it means that in vision sensor, we'll have only the fixed resolution one. Whereas for camera, it can be adjusted. Like, while doing the focus and all that stuff, you can adjust the resolution accordingly. So this one is the example for a perspective vision sensor, which will be having like angle. So there is another kind of vision sensor, which is called orthographic vision sensor. So I'll be showing you that too. So we'll be adding a view for this. And we'll be moving the vision sensor and we'll be playing. See, now you can see that this is the orthographic. So what's the, you have seen this both, right? What do you think the difference between orthographic and this perspective vision sensor? I think you now got an idea like how this works. Can you say me like what's the difference between like perspective and orthographic? It has been zoomed out? Not exactly. See the shape. Let me add a orthographic also here. You'll understand. It has been zoomed out and blurred.
No, zoom and
No,
blur
we
is fine.
can, that one we can adjust accordingly actually.
Yeah, blur depends on the resolution actually. If the image is more blur, that means it has very less resolution. If it is more clear and pixel perfect, that means it takes more resolution and more size to store. That's why. What are those blue lines? Those blue lines are like the range of the camera
So
it can see.
yeah, that's the answer exactly. So see, this is the perspective vision sensor and this is the orthographic. Okay, for orthographic, you will have a similar field view. Okay, you will be having the parallel field view, whereas for perspective, you will be having like a focused one. See, from here to here, it's like diverging. The viewpoint is diverging. So perspective vision sensors can be used for far away distances. Like they will be more focused and all the stuff. And for orthographic vision sensor, we can use it for more of a clarity. Like it can be used for specific objects. To focus on a specific object, we'll use orthographic, and perspective depending on use, left, how much a distance we are placing an object and all that stuff. We can use the perspective vision sensor. These are the two types of vision sensors we use. And now I think you have known inverse kinematics and forward kinematics in previous classes, right? Can you say me the differences between inverse kinematics and forward kinematics? So what do you think is forward kinematics? Any answers? I think in previous sessions we are, discussed more on forward and inverse kinematics. What are they?
Guys, unmute and say the answer. It's okay. Why? Because the answer is too lengthy to type, so you can unmute and speak.
So yeah, we'll get started. So here, this is a DOF manipulator, which is one kind of robotic arm, and here we use inverse kinematics. The main idea of inverse kinematics is here the external object, using an external object, will calculate the torque internally, and the robotic arm moves accordingly. Okay, so I think you got confused by this definition. Let me demonstrate you. So we are simulating this, and this is the object. Okay. So see this. I am moving the object and robotic arm is moving accordingly. It's calculating its torque and forces and all other things with respect to this object. You can see, right? So it's moving wherever the ball goes. So this is called as inverse kinematics, where we are like with respect to the object, the robotic arm is adjusting its forces and torque. There is something called as forward kinematics. Do you know what's forward kinematics? So this is a robotic arm UR3. Here they will use this forward kinematics. For forward kinematics, we need not to use any external object to move it. It has its own path. Let's see this. See, once we on the simulation, the paths are like moving. You can see this, right? So these parts are moving. So this is like like even though there are no external objects, it has the internal forces and torques which is resulting in the reaction forces. So it's called as like a forward kinematics. So here this is an UR3 arm and this is an DOF arm. So now we have seen sensors and joints and all. Now we'll be seeing where the joints and sensors will be used in robotic arm. So see this dynamic. Now you can see these joints, right? So these are the joints we'll be using in this board. We are using these joints, revolute joints. So we'll be okay. Forward kinematics takes us input. Yeah, exactly. It will be taking input joint angles. Actually, I think that's the inverse kinematics. It takes with respect to the foreign object. You know, Avantika. It's like as we see in DOF manipulator. It will be calculating the Cartesian position of this green ball and it will be adjusting the joint angles and everything regarding it. But forward kinematics will have it like inbuilt, like it will be having beforehand itself. It is not calculating at all. It will be having all the internal torques and internal forces. So that's the thing. So next thing is like now we'll be seeing how these joints and stuff is used. Now you can see these joints and all, right? So these are all the revolute joints and here we use mainly revolute joints. So these joints are used for movement and all the stuff. Yeah, the yellow ones are the joints. So the yellow ones are joints and these red ones are dynamic objects. What do you mean by dynamic object? Dynamic objects is like, you know, the object which in simulation world, there are something called as static and dynamic objects. Dynamic objects will have the effects like collisions, movement, etc. Static objects are like, you know, some rock or it will be just staying stable irrespective of whatever environment is happening. Dynamic objects will be, you know, it reacts with the environment and produces the result accordingly. So let me show you another example. I think you can see this board, right? See, this is moving with respect to revolute joint and it's moving here with respect to prismatic joint. So here this down part is like static object and this part is like dynamic object and the yellow joints here are hidden normally. Normally, even if you want to see, you can see for other where it's not hidden actually. So these are the joints we'll be getting through it. So this is how we will do simulation in a virtual world. So in Cochlear Sim, this is how you will do simulation. As Karthik said before, based on your problem statement and all the problem statement and you know the procedures, everything you want to do, you will create a blueprint, right? Like what you want to do and everything. You can design your own parts and import it and you can assemble and you can make your things work here and you can even check all the simulations. See, when you start the simulation, you'll have something called as a real time and the simulation time, which means like what happens in real time and the simulation. So the simulations are not exactly the real world situations, but it's slightly, we'll get a basic idea like how it works in real life. That's what. So that is for today. Now over to Karthik.
Yeah, guys. So, uh, do you want anything like in that Copliasim software? Do you want us to make any other simulation, like any sensor or something?
Guys, do you have any doubts on this, like regarding cochlear seam? Like, I mean, how you do you have any problem in understanding?
Do you have any doubts in this up to like the designing of a robotic system? These slides. Anything you can ask anything, even if it is a silly one. It's clear. Thank you.
So, just an icebreaker question. Guys, we have seen some procedure of designing a robotic system, right? Like, can you make your own problem statement relating to something called real life? I just now got a statement like Karthik said a table fan, and we can also create like we have seen outside like some automatic. Whenever we enter room, some lights will on automatically, and when we go out, it will switch off, and some kind of robotic systems and all that stuff. Do you have any ideas on that, like can you frame any ideas on that, like problem statements regarding your our
Summary of step to design. Yeah, fine. We will go with that. And as I told, it is a 6-step process. So if you want to convert any machine to a robot, you have to do these 6 steps. The first one is defining the problem and analyze the objective correctly. That is, like in the analysis part, mainly consider the environment where we are using that robot. So in the case study I have given, we have to convert the table fan into a robot in our room, like in the room we usually live. So that is the environment. Suppose I want you to make a robot which will work in factory, the environment will be different and the sensors you will be using will be different. So identifying the environment and identifying the correct sensors you want to use is the main thing. In second step, you will do research and designing. This is like you will be searching for the sensors, the stable designs, stable models and all. See, now you have seen some robotic arms, right? In the Cochlear Sim. So those are some stable designs. Last year we designed a robotic arm in that same Cochlear Sim software. There, when we started working on the design, the base was so unstable that it used to fall down when we move any part. So we have to optimize the design. Then we stabilized the base, each part and all. Same like that, even for the stable case or any other case, you have to do what you have to do is you have to make a stable design which can sustain basic problems and basic environmental issues and all. So that falls under research and design. Third one is creating a prototype. Creating a prototype means making a simulation if necessary, then making a sample, and then making the real model. And fourth one is programming and testing. So once you create your prototype, like you attach all the bolts and nuts, you attach all the parts, everything to the everything to a single piece, then you have to write code for that. You can't write a perfect code in single shot. I am pretty much sure of that. So even any one of us do, what we will do is we will write a code, we will upload it to the board, we will test whether prototype is working. If it is not working, then we will debug the code. We will find where the error is. We will correct the code again. That is like the programming and testing case. So we will program, we will test. If the test is successful, we will move to next step. And if the test fails, then we will do the program again, upload it again, test again. And the next step is building your robot. Like once your prototype becomes successful, and if you enter this step, you can get the required hardware things like all the hardware components, objects, dynamic objects, everything you want, and then you can start assembling each of them. And the last step is evaluating your robot, which is like observing the performance actually. maybe in some cases your prototype may work, but your main model might not work. In that case, you should be able to find where the problem is there, and you have to correct the problem, and you have to do it from the prototype stage so that it will be more stable. So these are the 6 steps. Do you have any more doubts in that?
So guys, just adding to that, we'll show you one of our model. It's not the final step, we'll show you the intermediate steps.
Yeah. Just a second, she will share the screen. Yeah. Yeah, so this is a robotic arm without a gripper. Actually, we added a gripper, but I think that file was not there. So here I told now at first, see, even it is not stable now. Why? Because this is like a failure model at first. Then we modified it a lot, and I think she don't have that file now. So here you can see the base, like which is thin and flat. The thing is, at first we made it so small. That's why the robot base is stable and it used to fall down every time. Then we increased the base, and you can see that red and blue color lines there, right? One wants show them the joints, revolute joints. Yeah, that red color and blue color one, that is a revolute joint actually. Uh, we attached a revolute joint there so that the robot can turn there. And okay, close. So that is the revolute joint, and we have some degrees of freedom. Like there is a term called degrees of freedom. To increase the degrees of freedom, you have to add more revolute joints to that. That is a robotic arm. We designed it for some competition named Yantra last year. Okay, so any doubts regarding these things on today's session? Anything? Or any suggestions, like any doubts, any unclear concepts? And yeah, these are us, like me and Banu Chandana, tutors. Will you please send that simulation?
Yeah, sure.
Yeah,
We will
sure.
send you like, the download link or something.
Yeah,
We'll attach it at the PPT or something and we'll send you.
yeah, we will
No
send it
worries.
through email or WhatsApp group. The thing is, see, if you want to design anything in simulation, what you have to do is you have to create a 3D model in Fusion 360 or some other 3D designing things. And after that, you have to load the 3D models into this Copliasim software. Then you have to attach each part. Okay, please fill this feedback form, which would be helpful for us to improve. And
Yeah. Guys, on adding that, see, it depends on your problem statement and what kind of robotic project you are gonna do, or like if you wanna do some hardware implementation or something for simulations. For us, robotic arm, Cochlear Sim is like the better option. And for other simulations like drone simulations and other things, we have something called UAV, open drone, and all other softwares. You can even check that. The thing is, you need to explore the things, and for building project you need to collect the resources properly.
yeah, and the question is, can you explain degrees of freedom once again? Yeah, so degrees of freedom, you can imagine it like the flexibility. In simple terms, it is like flexibility. So how I can say is, if you Google that, there will be a complex, like not complex, there will be a weird thing like the maximum number of logically independent values that have the freedom to vary in the data sample. So that states the degree of freedom, which is very confusing for me too. So let me explain in my terms. It is like, did you study it in chemistry or somewhere about the degrees of freedom? Anyone? Actually, in chemistry of class 12 also we have that concept. So degrees of freedom is like the number of ways you are allowing a particle or any object to move. Like if you allow an object to move in straight line only, it is degree of freedom one. Degree of freedom will be one. If you are allowing it to move it, this photo. So if you are if you are allowing it to move it on a plane only, then the degree of freedom will be two. And like if you are moving it in 3D, then the degree of freedom will be 3. And you can imagine like how degree of freedom will be 4. Like we have only XYZ axis. You can see here. See, you have forward, you have left and right, and you have top and down, which is like 3D. And while moving these three independently, you can roll the object. That is like degree of freedom will be 4. And if you are rolling the object in 2 directions, the degree of freedom will be 5. Uh, did you understand what I am saying, or should I go to layman terms? Okay, wait. Okay. I'll do one thing. Consider a cricket ball first. You consider a cricket ball and imagine like it is moving exactly on a straight line. It can move only on straight line. And if it moves on straight line, that means its degree of freedom is 1 in that case. And if it is moving on a plane, like you rolled it on your home like floor, then its degree of freedom will be 2. If you are throwing the ball correctly without any turnings and all on the ball onto space, like onto air to someone, then the degree of freedom should be 3. But while you are throwing it, the ball will start turning it around itself, right? So including the turning, if it is turning only in one direction, the degree of freedom will be 4. And if the turning is like also in double, which is not actually possible, but if you can turn that object in both front and right side also, while it is in air, then you have 5 degrees of freedom. 3 degrees of freedom for 3 XYZ axis, 1 degrees of freedom for rotating it in one direction, and 5th degree of freedom for rotating in another direction. So that is degrees of freedom. I think everyone understood. So you want us to explain any other terms? Guys, is that clear? If you have any doubts, you can unmute and ask. And if you have any doubts, you can put it in chat box also.
So guys, adding to that, so as I said you before, try to frame a problem statement, and in next session we'll discuss more about it. Okay.
Yeah, like what she's saying is consider a machine, try to make it as a robot, and we will share you the PPT actually, like the 6 steps of process. And if you follow the 6 steps, like tell us like what you are doing in each step, like what sensors you are using, what sensors you rejected to make that machine as a robot. And if you try that once, like you will understand how we design a robotic system actually. Okay, right? We will share you the PPT also. Once try that, like try to create a problem statement. And if you are stuck anywhere and if you have any doubts, you can ask us anytime through WhatsApp or email or anything. Even